So, the first part of this chapter, it's hard to imagine, but in a sense, we've only actually gone through 3 lessons. But they're such foundational lessons that with every one of them, I've been splitting them up into 2 sessions so that we can kind of focus on one part of the lesson for one day and then focus on another part of that lesson for another day. And so we're actually doing that with 2.3 as well. But with 2.3b, I think what you're going to find is a lot of what we've talked about in our previous lessons up to this point in the chapter, it's going to get sort of pulled together and tied in today. We're going to be pulling some things from what we did with right triangle trigonometry. We're going to talk a little bit about some stuff from last class. And we're just going to kind of pull stuff together now into ultimately what we want to be able to do when it comes to finding the trig functions of any angle. Okay? So be prepared. Get your thumbs licked, because we're going to be turning pages back and forth and going back to some of our previous notes and pulling it in here and then relating that to something from another set of notes and pulling that together and things like that. So we're going to be turning back and forth quite a bit today. So what we're really going to be focusing on today is not so much any angle, but any angle among the special angles. So if you remember, when we were talking about right triangle trigonometry, we took a little bit of time and talked about the special angles from the special triangles, the 30, 60, 90, and the 45, 45, 90. And we kind of went through the process of figuring out what the trig functions for those specific angles were. Well, those special angles from the right triangles are a basis for the special angles that we have when we're talking about rotation around the entire circle. And so we're going to build on what we've already talked about in terms of special angles from right triangles and expand on it today. Okay? So if you look back at your right triangle notes, there we go. Okay. We had the 30, 60, 90 triangles. We had the 45, 45, 90 triangles. And so in order, we've got the 30 degrees, the 45 degrees, the 60 degrees, and then actually 90 degrees is also a special angle. We didn't really figure out the trig for it when we were talking about it in terms of right triangles, because we could only figure out the trig for the acute angles in a right triangle. But 90 is actually one of the special angles. And so we're going to add that to our list here. Now what I would like you to do really quick is take a minute and convert these into radians. This is what we were talking about as degree measures, but what would these be as radian measures? Take a second and write down what they should be. Okay? All right, so in radian measure, 30 degrees is equal to what, Nicole? Sorry?
5/6. Wait.
5/6? Okay?
Yeah.
All right, 45 degrees, Alton. 60 degrees, Morgan. 5/3. And 90 degrees, Alfred, what 90 going to be? 5/2. Okay? So those are the radian equivalents for the degree measures that we talked about when we talked about them as right triangles. We are going to focus on them as radians today. Okay? And I think you'll see why as we go through. There are a lot of patterns and different things that happen when we're talking about radians that make doing this a lot easier than when we consider them as degrees. So we're going to focus on these special angles as the radian measures today. So pi/6, pi/4, pi/3, and pi/2. Okay? All right, so we did this a little bit in a previous class. We talked about the circle and rotating around the circle, and we identified some of the significant angles, I guess, around our rotation. Well, those significant angles were all multiples of these special angles in radian form. Right? So when you look at this circle, which is also on the worksheets that I handed out to you, you should have a worksheet in front of you that has a table on one side and then a circle like this on the other side. So start with this part. So you can see here that they've started to label some of these. We're starting here at 0 in standard position, just like we always do. And then as we start rotating, you can see we've got pi/6 and pi/3 and pi/2, and then we've got 2 pi/3, which is just a multiple of the pi/3. And we've got 5 pi/6, which is just a multiple of pi/6. And pi is really just a multiple of pi/2. So a lot of these particular angles that are labeled around this circle are simply multiples of the special angles we were just talking about. But we're missing one. Which one are we missing? Which special angle is not on your circle right at the moment? Which one of those are you not seeing? Pi/4, right? So where does pi/4 go?
In between pi/3 and pi/6.
Okay. So on your papers, I would suggest you draw in an additional line. Right there between pi/6 and pi/3, and label that pi/4. Okay, and then we need to do that in the other quadrants as well. So I'm going to split right down the middle of the 3 and 6 multiples here. split right down the middle of the 3 and 6 multiples here, and split right down the middle of the 3 and 6 multiples there. When I mean 3 and 6, I'm talking about the denominator. Okay? Now, if we label the rest of these, if this is pi over 4, as I rotate around that far, if I make an identical rotation from there to here, then I am in a sense doing 2 pi over 4, but that actually just reduces to pi over 2, which we already have labeled, right? If I do another rotation of the same amount, then where am I at? 3 pi over 4. So that's what we're going to label this one. Same amount of rotation gets us here, which is 4 pi over 4, but that's really just pi. So that's already labeled. Another rotation puts us here, which would be 5 pi over 4. Rotate again that much, we get 6 pi over 4, which is going to simplify to our 3 pi over 2. And then one more rotation of that much is how much? What should I label this one? 7 pi over 4. And then finally, one last rotation would put us at 8 pi over 4, which is really just 2 pi, so it gets us back to the start. Okay, so you now have a circle with the 16 special angles labeled on it. And it's these 16 special angles that we have to get to the point where we just know these, where we can figure them out within a 30-second time spot. Like we can just boom, boom, boom. I ask you what the sine of this is, you tell me. I ask you what cosine of this is, you tell me. Like, it's got to become automatic. It may not be yet by the end of today. It may not be yet by the time you get done with your practice, although it should be getting a little closer because that's mostly what your practice is going to be about, is just evaluating trig functions. But definitely by the time we get to the test, you got to know these. You just got to be able to, yep, it's this, it's this, it's this. Okay, so what we're going to talk about today is a little bit of what the trig functions are and how you get them. And it's in that how you get them that I think you'll start realizing that this is not really so much a memorization task that I'm asking you to do. Or let me put it this way. It doesn't have to be. I mean, you could sit down and memorize all of the trig functions for all 16 of these. I wouldn't want to, but you could. But it's not necessary. Okay? We can start looking at how all of this works and realize that there's certain patterns to it all, and we can actually narrow down what actually needs to be memorized to very little, and then use all of these relationships and patterns and everything else to figure everything else out. So that's kind of what we're going to talk through today, is what are all of those relationships and patterns so we can use them to our advantage. Okay? All right, so this is kind of taking that right triangle trig that we did at the beginning, and it's pulling it into this idea of the rotational trigonometry and expanding it from just the 30, 60, 45, and 90 to include the entire circle. Okay, but it's all based on that 30, 60, 45, and 90 that we started with in right triangles. Okay? Now, let's go back not quite so far to just last class, where we had this screen. This is what we concluded after we looked at angles that were created by rotating our terminal side and knowing that our terminal side went through a particular point with x and y as coordinates. Right? And so what did we say that we would have now as our ratios for our trig functions? To find sine, we would do what? Y over what? R. For cosine, x over r. For tangent, y over x. For cosecant, secant, and cotangent. Right? And how are we going to get r? Okay, so do you remember the formula that we wrote down for how to get that?
Square root of x squared plus y squared.
Good. Okay? So that's what we talked about last class. We've got our terminal side, we know it goes through a particular point, and based on the coordinates of that point, we can find r, and then we can set up the ratios. Okay? Well, if we go back to this idea of the circle, what oftentimes happens is that mathematicians, contrary to popular belief, mathematicians are always trying to find ways to make things easier. Now, most math students are convinced that mathematicians' jobs are to make their life more difficult. It's not true. Mathematicians' job is to try to figure out, how do I use math to make things easier, to simplify it, to make it more elegant, to make it more efficient, that kind of thing. And so mathematicians said, well, you know, in the scenario like we were talking about last class, where we start here at the initial side, and let's say we have a point that's right here on that terminal side, and as it starts rotating, it's going to, if we imagine it has some ink under it or some paint, it's going to create this circle as it rotates around. Whoops, got really sadly off. Let's try that again. Okay, so it's rotating, 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 and back where we started. So that dot is creating this circle as we go around. And basically that point then is the point where the terminal side has intersected with the circle. Okay, make sense? And so then R is what we have to figure out in terms of what is that distance from the origin out to that point. And mathematicians said, well, what if we just arbitrarily made that 1 unit? What if we just said r is going to equal 1? What we now have is what they call a unit circle. A unit circle is simply a circle with a radius of 1. Okay? And so this unit circle idea comes into play a lot with trigonometry, because by making r equal to 1, we can go back to our ratios and we can make them even more streamlined. Right? Every place I now have an r, I can replace it with a 1. So there, and there, and there, and there. Doesn't really affect tangent and cotangent because there wasn't any r's involved. But it does affect my sine and cosine, and therefore my cosecant and secant, because now, what is the sine of theta going to have to equal? Y over 1 is y. So now we're saying, if I know that I'm dealing with a unit circle, I know that the radius of this circle is 1, then that means whatever my y coordinate is, that's the sine of the angle. End of story. I don't have to make it any more complicated or, rationalize radicals out of the denominator or anything like that. It just is whatever the y coordinate is. Same thing with cosine. Cosine now just is whatever the x coordinate is. And then tangent is still whatever y over x would be. So by simplifying the idea of rotating around the circle to making it a circle of radius 1, we have also now simplified the idea of what sine and cosine should be. They're just going to be whatever the coordinates of my points are. Okay? So, if I were to rotate this a bit, and let's say I end up at pi over 3 is my angle. This point, as I rotate it around, and it ends up right here, that's, again, the point where my terminal side and my circle are intersecting. It would be some x comma y point. Which now means, because r is still 1, it now means that it is cosine of theta, comma, sine of theta. That's the ordered pair. And so the beauty of that is you can go back and forth. If I know what the sine and the cosine of pi over 3 is, those become my x and y coordinates. Or if I know what the coordinates of that point is out there that gives me a radius of 1, that becomes the sine and the cosine. We can go back and forth with that. And that's going to help us to figure out the trig functions for all 16 of these different angles on this unit circle. Okay? All right, so flip your paper over to the table. And then flip in your notes back to right triangle trig for a minute. Okay. So the first thing I want you to do on this table is I want you to fill in this row that's labeled positive radians. So if you're going in the positive direction around the circle, what is the radian equivalent for each of these degree angles that are in the second row? Now, we've already talked about some of them, so let's go ahead and fill those in. Obviously, 0 degrees is how many radians?
0.
0, that's easy. Hang on a second. I think I want to get this then again so it fits better. And 30 we just said was what? Pi over 6. 45 is? Pi over 4. 60 is? Pi over 3. And 90 was? Pi over 2. So we've already established those. Okay, now take a minute and keep going. Try to fill in the rest of the radian measures. And you can do this however you want. You can grunt it out with converting equations. You can look for patterns. You can look at the circle on the back side if that helps. You can do whatever you need to figure out what the rest of that row should be. But try to figure it out as quickly as you can. Okay? All right, let's start filling them in. If you're not quite done, you can fill them in as we go. So 120 degrees, what should that be? Schaefer, did you get it?
120.
120.
2 pi over 3.
2 pi over 3. Okay, 135 degrees. Emily?
3 pi
3 pi
over 4.
over 4. 150 degrees. Lauren? 5 pi over 6. And then 180 degrees. Michaela?
5.
Pi. Okay. Now, just go. How did you get it? Yeah, same thing, that's fine. If you just look at that first half of the circle, just that top half, do you start seeing any patterns? See anything that looks like it's creating a pattern? No? Alright, well let's keep grunting it out then. 210. Anybody? 7 pi over 6. 225. 5 pi over 4. 240.
4 pi over 3.
Whoops. I can salvage it. 4 pi over 3. 270.
3 pi over 2.
3 pi over 2. 300.
5 pi over 3.
5 pi over 3. 315.
7 pi over
330.
11 pi over 6.
And 360.
2 pi.
So now that we've got the whole circle up there, do you see any patterns emerge? Nothing? Really?
the denominators on the two sides of this in the same order.
Okay. And even within each half, what's happening with the denominators? 6, 4, 3, 2, 3, 4, 6. Right? There's even a pattern within each half. So 6, 4, 3, 2, 3, 4, 6. 6, 4, 3, 2, 3, 4, 6. It's not a coincidence. Okay? So use that pattern. It's what you see on the circle side as well. 6, 4, 3, 2, 3, 4, 6, nothing. 6, 4, 3, 2, 3, 4, 6, nothing. Okay? Now, which of those is not in a quadrant?
0.
0?
90.
Which one?
90.
90, pi over 2.
360.
360, way down here. 2 pi. 180, pi.
270.
And 270, 3 pi over 2. So on those that are not in a particular quadrant, up here in the quadrant row, we want to label them by what axis they're on. So 0 is on the positive x-axis. Pi over 2 would be what?
Also the y-axis.
The positive y-axis. How would you describe pi? Negative x-axis. Good. How about 3 pi over 2? Negative y-axis. And then 2 pi, we're back to 0, so we're back to being on the positive x. Okay? So if those are the angles that end up on the axes, then the angles in between must all be in the same quadrant. So these three angles are all in which quadrant? 1. And then these three angles are in 2. And these three angles are in 3. Which leaves these three angles to be in 4. Okay? Alright, so on your right triangle trig notes, find the trig functions that we did for the 30-degree angle. Okay, everybody got it? Because I don't want to work these out, I just want to write down what we've already done for work before. Okay, so we're going to skip this reference angle line for just a minute and start with sine. So what was the sine of 30? 1/2. The cosine of 30? √3/2. Tangent of 30? √3/3. Cosecant of 30? 2. The secant of 30? And the cotangent of 30? Okay, so the fact that we're now talking about this angle in terms of a radian measure instead of a degree measure doesn't change the trig of it. Because the trig is about ratios of sides. So as long as the measurement of the angle is the same, how we talk about it doesn't change what the trigonometry is going to be. So we can use the trig that we already figured out from the right triangle trigonometry when we said it was 30 degrees, and that's the trigonometry that's going to hold true for pi/6, even when we're talking about it in the rotation of a circle rather than in the right triangle. It's all the same. Okay, let's go with 60, since that's probably in the same place in your notes. What is sine of 60? Oops, hang on a second. I want to make this skinnier so it fits better. Alright, so √3/2. Cosine of 60? 1/2. Tangent of 60? √3. Cosecant? Secant? And cotangent. Please tell me that Emily's not the only one who has this in her notes. He's the only one I'm hearing. I hope that's not an indication that you didn't take this down the first time around. Alright, now what about 45? Pi/4. What's sine of 45? Thank you. Whoops, but that's thick. I want thin. It's like ordering pizza. There we go. Alright, √2/2. Cosine? Also √2/2. Excellent. Tangent? 1. Cosecant? Secant? Cotangent? Okay. Alright, so that's just pulling in what we already knew from what we did with right triangles. But now we need to expand on that. Now we need to build on that. So I want you to skip 90 degrees for just a second. And I want you to think about the 120 degrees, the 2pi/3. We go back to our circle here. 2 pi over 3 would be this angle right here. Wow, I drew that really skinny, or crooked, but pretend that's a straight line. Okay, that's where 2 pi over 3 as an angle would be. Right here is the point we're talking about in terms of the xy over ordered pair, where the terminal side would intersect with the circle, all of that. So this is the angle of 2 pi over 3. What is the reference angle? How much? Pi? Okay, so that's where it is, right? From here down to pi, that is where my reference angle would be. But how much is it? What is that actual angle? Two pi over 3 is this much, the red. So what's the blue going to be? Pi over 3, right? Because I need 3 pi over 3's to get all the way over here to pi. So if the red is 2 pi's over 3, this must be an extra pi over 3 in here. So we know the reference angle is, again, that acute angle that's created by our terminal side and our x-axis. And in this case, if my angle is 2 pi, my reference then would be 2 pi over 3. Then my reference is going to be pi over 3. So here, my reference angle is, okay, that didn't work so well, let's try that again. Pi over 3. Okay, do you see any connection between my angle and my reference angle? Based on that connection, what would you guess the reference angle of 3 pi over 4 is? Pi over 4. What would you guess the reference angle of 5 pi over 6 is? Pi over 6. Isn't it a beautiful thing? It's one of the reasons why we use radians. Because whatever the denominator is on our angle, when we're talking about these special angles, the first quadrant angle with the same denominator becomes our reference angle. So I can keep going here. 7 pi over 6, what do you guess that the reference angle is going to be?
Negative pi over 6?
Nope. Don't overthink it. 7 pi over 6, what's the reference angle? Pi over 6. 5 pi over 4, what's the reference angle? Pi over 4. 4 pi over 3, what's the reference angle? Pi over 3. We're skipping the axes for the moment. 5 pi over 3, what's the reference angle going to be? Pi over 3. 7 pi over 4. And 11 pi over 6. The reference angles are going to be acute angles, which basically means we're always going to go back to one of these in the first quadrant. We don't have to make them negative. We don't have to do anything fancy. All we really have to do is match up denominators. Okay, so if it's 4 pi over 3, it's going to be pi over 3 as the reference. If it's 7 pi over 4, it's going to be pi over 4 as the reference. Easy peasy. Don't make it any more complicated than that. Okay? Now, how does that help? Well, once I know what the reference angle is, remember when we were doing these problems last class? Once I know what the reference angle is, I know that the numbers from the reference angle give me the numbers for my actual angle. Right? Whatever the trig was for the reference is what the trig is for the actual. Okay, so if my reference angle is pi over 3, then that means the numbers for 2 pi over 3 are going to be the purple ones. The same as what pi over 3 was. Okay, I'll write those down. Do it. So, I'm just going to copy these. Square root of 3 over 2. 1/2. Square root of 3. 2 square root of 3 over 3. 2 square root of 3 over 3. Numbers wise, we match up exactly with what the reference is. But then what's going to change is what's going to be positive and what's going to be negative. Right? Because it's only in the first quadrant where everything gets to be positive. I'm now over here in the second quadrant. So now we got to start thinking about positives and negatives as well. So, in the second quadrant, which trig function gets to stay positive? Think about your saying. Sine. All students take Chinese. Students is in the second quadrant. That's sine. So sine and what else actually gets to stay positive? Sine's going to stay positive, but what else gets to stay positive? Not cosine, cosecant, right? Because it's the one that's just the reciprocal of sine. So if sine's positive, cosecant has to be positive. But everything else has to now turn negative. So cosine's going to be negative, tangent's going to be negative, secant's going to be negative, cotangent's going to be negative. Those are now the actual trig functions for 2 pi over 3. So as we expand beyond just the first quadrant and just those 30, 60, 45, and 90-degree angles we were talking about with right triangles, it basically comes down to 2 things you have to identify. The first part is the number, and that's going to come from what your reference angle is. The second part is the positive or negative sign you should have on it, and that's going to come from what quadrant you're in. You put those 2 pieces together, you've got your trig functions. Okay? So let's try the next one quick. If I want the trig functions for 3 pi over 4, we've already said the reference angle is pi over 4, so let's go by color. If these are what I'm starting with, which color should I write down in that column? The blue ones, right? Those are the ones that came from pi over 4. That's my reference angle. So I'm going to write down the blue ones. Oops. There we go. Okay, so that would be a square root of 2 over 2. Another square root of 2 over 2. A 1. A root 2. A root 2. And a 1. Which quadrant are we in? 2. So which ones get to stay positive? Sine and cosecant. And so everything else becomes negative. There's our trig functions for 3 pi over 4. Make sense? Okay, now let's go back to pi over 2. That one's a little bit strange because it's right on an axis. And when we were doing right triangles, we never found our trig functions for 90. Okay? So for this, we need to go back to our picture for a second. If I'm talking about an angle, that started here. I think. Let me guess. Now it's finally going. Oh, I love this. Okay, make that a little thicker. So if I start here and I go pi over 2, I'm going to end up there. And this point that's tracking and making this circle ends up right there. Can somebody tell me the ordered pair for that point? Any guesses?
0.
Why do you think it's 0, 1?
Because if you think of like the lines as like x and y axis,
Yep.
that one, it starts at the origin for the x-axis, and since r is 1, y. Wait, since r equals 1, which is like the length that one, and then circles, all the radii are the same length, so that one would also be 1.
Exactly. Yep, good. So it's 0, 1 because we're right on the y-axis, so we didn't go anywhere left, right if we consider the center to be our origin. And we're still talking about a unit circle, so we're still talking about a radius here that's 1. So the amount that I went up had to just be 1 unit. Okay? So I can identify that point as the ordered pair 0, 1. What does that tell me then about the cosine of pi over 2? Hint is up here. If I know the ordered pair of that point where the terminal side intersects with the circle is 0, 1, what does that tell me about the cosine of my angle? And what does it tell me about the sine of my angle? It's 1. So remember, we just made this connection. Because r is now 1, we can now say x and cosine are the same. They're equivalent. Y and sine are the same. They're equivalent. So if I know the x and the y of this point, I know the cosine and the sine, respectively. So the cosine would have to be the 0, and the sine would have to be the 1. And the nice thing is they both go alphabetically. So we're already pretty familiar with its x comma y. Okay? If you are talking about the ordered pair in terms of trig functions, it always goes cosine comma sine, because it also goes alphabetically. So cosine is always your x-coordinate, sine is always your y-coordinate. So if I go back to our table here, that means that the sine of the pi over 2 was the 1. It was our y-coordinate. The cosine of my pi over 2 was the 0. That was my x-coordinate. Now what's tangent going to be? How do we find tangent? How do we find tangent? Y over x. So what was my y value? What was my x value? So what's y over x going to be? Undefined, right? Because if x is 0 and x is in the denominator, I can't do that. I can't have a 0 in the denominator. So tangent gets a little funky sometimes when we're on the axes. Because it's on the axes where one of our coordinates could be 0. And so if that 0 ends up in the denominator, we get undefined answers. How about cosecant? One, right? Reciprocal 1, 1. What about secant? Undefined, because taking the reciprocal of 0, we put 0 in the denominator, so that's undefined. How about the cotangent? Not quite. 0. Because if you go back to that x over y ratio, putting 0 over 1 works. So we don't want to rely on the fact of, well, if that was undefined, my reciprocal must be undefined. We have to kind of go back to the ratio itself. X over y would be 0 over 1. That would be 0. So that's what the trig for pi over 2 looks like. And then we can do a similar thing for 0. I wanted to just keep everything right here at my initial side, standard position, don't rotate at all, have an angle of 0, then this is the point right here that I'm interested in. Well, what's the coordinates for that point? What do you think? 1, 0. Yeah. Because now I've gone to the right 1, but I haven't gone up or down at all. So if we come back to our table for 0, the sine would have to be what? 0. The cosine would be 1, and the tangent would be 0. Yeah. Because this time y over x would be 0 over 1. That's doable. That's just a 0. Now if I do cosecant, that one's undefined. Secant, 1, and cotangent, that's the one that's undefined too. Yep. So when you're on the axes, you are probably going to end up with some of your trig functions being undefined. It's just a matter of which ones are undefined based on which coordinate was 0. Okay? So that should be enough info to allow you to fill out the rest. Find the patterns, use them, think about numbers, and think about plus or minus signs, and fill in the rest as part of your homework. Now, one other quick thing I just want to show you. So we've been talking about this idea that if you're trying to do the trig functions for an angle, that it's about two things. Figuring out the number you need based on the reference angle, and figuring out the positive or negative you need based on what quadrant you're in. Well, there's a kind of cool little trick for doing that called the left-hand trick. Has anybody heard of this? All right, so left-hand trick. The idea is this. Something like that. If you imagine your left hand, you're going to imagine axes. And so your x-axis is going to be your little finger. Okay? And then up and down here, your thumb is going to be your y-axis. Which means this is a 0 angle, and this is a pi over 2 angle. Okay? So 0, pi over 2, x and y. Now when you look at your circle, how many of the special angles are between 0 and pi over 2? How many do we have in between? How many? 3. Pi over 6, pi over 4, pi over 3. How many fingers do I have left? 3. Guess what they represent? Pi over 6, pi over 4, pi over 3. Okay? So each finger is going to represent the specials that are in between 0 and pi over 2 in the first quadrant. So pi over 6, pi over 4, pi over 3. Okay? All right, so here's what you do. First of all, you take a look at 2 pi over 3. What's my reference angle? Pi over 3. Okay, which finger is that?
Index.
Your index finger. So you take your hand and you fold down your index finger. Okay? Now that you folded it down, think of it like a comma. Your comma has just separated your ordered pair. X, Y. Cosine, sine. So the fingers that you have to the left of your comma are going to represent finding cosine. And the fingers that are left to the right of your comma are going to represent finding sine. Now how do you actually find it? For sine and cosine, you're going to take the square root of the number of fingers over 2. Because if you go to this table and you look at all the answers we get for sine and cosine, they're all over 2. Except for 0 and 1. But everything in between is always over 2. The choice is it 1 over 2, square root of 2 over 2, or square root of 3 over 2? Right? So on my fingers, if I put down the pi over 3, then how many fingers are left to the left? How many fingers are left to the left of my finger that's down? Really? Thumbs get to count as fingers in this. There's 1, right? There's 1 still sticking up here. So that means for cosine, right, because it's the first of my ordered pair, for cosine of pi over 3, we're going to have the square root of 1 finger over 2. Well, what is the square root of 1? 1. So I get 1/2. Isn't that what we said cosine of pi over 3 was? Pi over 3 cosine 1/2. Okay? The sine of pi over 3 is going to be based on the fingers to the right of my comma. So how many fingers are still left over here on the right side? 3. So square root of fingers, 3, over 2. Isn't that what we said sine of pi over 3 was? Square root of 3 over 2. Okay? So to get the numbers, I can use this little trick and come up with 1/2 and square root of 3 over 2. To get the signs, positive, negative signs, I now have to think what quadrant is 2 pi over 3 in? Which quadrant are we talking about? It's one of the specials. You got to get better at this. 2 pi over 3. Which quadrant is it in? 2. It's over here. So if I'm in quadrant 2, is cosine positive or negative? Negative. Is sign positive or negative? Positive. So for 2 pi over 3, I get a negative 1/2 and a positive square root of 3 over 2. Okay? And then you can actually use this for tangent as well. For tangent, you say the square root of the right side, the sine, the y, right? We need y over x. So I take the square root of the right fingers over the square root of the left fingers. Okay, so again, if pi over 3 is the one that's down, that means it's the square root of 3 over the square root of 1, and square root of 1 is just 1, so I end up with square root of 3. X, y, cosine, sine, y over x for tangent, it's square root of 3 over square root of 1, which simplifies to just square root of 3. And you can do that with any of the specials. I can ask you for the cosine of 7 pi over 4. Okay, well what's the reference for 7 pi over 4? Pi over 4. Which finger should I put down? One, two, three, four, 5. Which one's going to be the pi over 4 finger? The middle finger, okay? So if I wanted the cosine of 7 pi over 4, I'm going to start with the cosine of pi over 4. What's that going to be? How many fingers do I have? I mean, this one's easy because I don't even care which side I'm on. It's the same. Technically, it's these right here. From your point of view, you're looking at these. It's the ones that are on the left side. The first one, comma, second. So cosine is going to be these. How many fingers? 2. So what is the cosine of pi over 4? Square root of 2 over 2. So what is the cosine of 7 pi over 4? Well, it's going to have square root of 2 over 2 in it. But now what quadrant is 7 pi over 4 in? The fourth. So in the fourth quadrant, is cosine positive or negative? Positive. So positive square root of 2 over 2 would be your cosine of 7 pi over 4. That's what I mean by ultimately what you have to actually memorize is not much. If you can use these patterns and these relationships, you don't have to memorize hardly anything. What you need to know is how do I find that reference that kind of starts the whole thing off, and then how is everything related to that? And if I wanted to find something really funky, like what's the secant of 2 pi over 3? Well, secant is related to what? Cosine. So find cosine first. That's the easy one. Cosine, okay, there. Now, take the reciprocal of it, you got secant. Boom, done. I don't have to memorize secant. I just need to know how to get secant. Okay? So, your practice today is mostly just practicing evaluating trigs of these special angles. I think there's like 15 problems there. You're just going to do a bunch. And tonight, it's probably still going to feel a little hesitant and stilted, and you're not entirely sure, and you're going to be figuring things out and looking at your fingers. And honestly, if you think that, oh, that's really like childish to be counting on your fingers and doing it that way, are you kidding? I didn't even learn this until last year. I stumbled upon it when I was looking for a video for something else. And this happened to pop up, and I watched the first bit of it and went, where has this been all my life? I'm 48 years old. I've never seen this before. Like, what? That's awesome! And you will see me now. If I'm like doing a key for trig stuff, I'll be sitting at my desk going, okay, so pi over 3 is that one. That's good. Okay, sine square root of 3 over 2. I use it, and I'm 48, and I'm a math teacher, and I've been doing this forever. So this is not childish. This is a quick tool to help you find a quick answer without having to go, okay, so did I memorize this correctly? Save that space for something important. Just use your fingers and figure it out. And even for the axes, it works. Because if I put down the thumb for pi over 2, what's to the right now? Left, your left, sorry. Right? This is your right. I'm so bad. Right? No, this is left. Okay, so I'm so directionally challenged. You should have asked my poor driver's ed teacher. So every time he'd say, turn at the next corner, I'd always turn the wrong way. So what's on the left side of this comma now?
Nothing.
Nothing. So what is the square root of nothing over 2? 0. What's the cosine of pi over 2? 0. We just got done saying that. Right? What's sine going to be? Well, how many fingers do I have left over here on the right side? 4. What's the square root of 4? 2. 2 over 2 is 1. What was the sine of pi over 2? 1. So it even works for the axes. It's awesome. Use it. Okay, but don't forget, it's twofold. You've got to use this to get the number, and then you got to know which quadrant you're in to decide positive, negative. Don't forget that positive, negative part, because that's important. So, lots and lots of practice. You've got the rest of your table to fill out. That'll be lots of good practice. And you've got the 2.3b homework practice in your book. Friday, we'll have a quiz up to this point. Okay? You'll have a chance to ask a couple questions first, and then we'll take a quiz over the 2-1, 2-2s, and 2-3s, the A's and B's parts. There's a practice quiz in your book. There's a practice quiz posted on Canvas, same thing, just if you forget your book. And the answers are posted on Canvas, so you can check yourself and see how you do. Okay, was there a question? Lauren, did you have a question? Okay.